Hello students, welcome back again. Now we will discuss a multi-conceptual question based on electromagnetic inductions. These topics involves are Lenz's law and its application, finding induced current in the coils, some questions based on magnetic flux and basic applications. So let's start. Now we will discuss some questions related to IIT-JEE. First question is, two circle coils can be arranged in any of three situations as shown in the figure. Their mutual inductance will be maximum in situation A, maximum in situation B, maximum in situation C, same in all situations. So we know that if in the coil 1 current I is flowing anti-clockwise, so we know that magnetic lines of force will be vertically up the plane like this. So means same lines of force will also pass through the area of the secondary coil. Due to that some current I will also induce in the secondary coil. So we need to find out mutual inductance. So we must understand mutual inductance M is equal to the flux involved in the secondary coil divided by the current in the primary, because it is due to the primary. So we need to find out mutual inductance. So mutual inductance will be maximum where flux is considered to be maximum. So we know that magnetic flux would be maximum when the magnetic flux would be maximum when magnetic field due to primary coil I1 into area of secondary divided by current. So we can say area is same everywhere in A, B, C, but we are changing the orientation of the primary coil. So it is clear over here that current or magnetic lines of force would be maximum reflected by A as compared to B and as compared to C. So magnetic mutual inductance will be maximum in case of primary or in case of option A. So we can say option A is the right answer. So key concept used in this question is mutual inductance directly proportional to the flux involved in the secondary coil, and that flux is a function of magnetic field due to primary coil into the area of the secondary divided by the current primary. So it is maximum reflect over here in the case 1. That's why A is the right answer. Now question 2. Question 2 is as shown in the figure. P and Q are two coaxial conducting loops separated by some distance. When the switch S is closed, a clockwise current IP flows in PSN in the figure, and an induced current IQ flows in Q. Now the switch remains closed for a long time when S is open. Case 2. When S is open, now a current IQ2 flows in this. So what we have to find out the orientation of current. Case 1 when switch S was closed. Case 2 when switch S was open. So this question is based on Lenz's law. In Lenz's law we know that let the switch S is closed at time t equal to 0. Switch S is closed at time t equal to 0, and it is given that direction of IP is clockwise. Now we have to find what would be the direction of IQ1. It is clearly reflected over there in concept of Lenz's law. Current flows in the secondary coil would be of opposing tendency due to which it is produced. So means current IP is flowing, causes magnetic lines of force through this. Now same line will also pass through the area of the secondary coil, and now the nature of this current would be opposite to the orientation of primary. So it is clearly this would be anti-clockwise. Now part 2, case 2. This is case 1. This is case 2. In the case 2 it is seen here when switch S is open. When switch S is open, they want to know the direction of IQ. Of course it would be clockwise then. It would follow the same concept. Means during the time the magnetic field due to IP from left to right increases at the location of lobe Q, According to Lenz law, the induced current IQ should be such that it tries to decrease the induced current IQ and should be anti-clockwise corresponding to this. So again it will follow the vice versa concept of Lenz law, and then we can say IQ2 will be again clockwise. Hence option D is the right answer, respectively anti-clockwise and clockwise. And the key concept used here is Lenz law. No need to confuse. Many types of questions are there. Case 1, current I is anti-clockwise. What would be the direction of current I2? It would be opposite to the orientation of primary coil. Question number 3, we will discuss here that a short circuit coil is placed in a time varying magnetic field. Electrical power is dissipated due to current induced in the coil. Electrical power. If the number of turns were to be quadrupled and the radius of the cross section of the wire is half, then electrical power dissipated would be what? So electrical power dissipated would be what? P2. So in this question we need to consider the magnitude of induced voltage is proportional. Induced voltage EMF is proportional to the number of turns, and also this induced EMF is due to the flux. So induced EMF is directly proportional to the number of turns. Also we know that R equal to rho L upon A, length and area, or we can say that is rho L upon pi R square, or we can say resistance is directly proportional to 1 upon R square, like this. Now we want to know the power. Power P is equal to voltage square by resistance R, and we know that voltage means EMF, or we can say E square by R. Now we can say it is directly proportional to N, capital N square divided by resistance R. Resistance R is 1 by R square. So we are getting it is proportional to N into R square. So we are getting power P1 is directly proportional to number of turns N1 and radius R1 whole square from this concept. Also the length function is there. Also the length, because it is given when the length, it is just doubled. So we can say NR by L, and this would be L. So we are getting power is directly proportional to number of turns into the radius square divided by length. Now we will draft this for two conditions: power P2 by power P1, that is equal to N2 by N1 whole square, radius relation as R2 by R1 whole square, and the relation of length L1 upon L2 it is, and this is equation number 1. Now we would like to relate it with, now if a wire of length L1, because length function is also there, so we can say that if wire of length L1 and radius R1 is stressed to a length L2 such that radius reduces to R2, then because we are talking about mass remain constant, so we know that mass is equal to density into volume, or we are getting density into pi R square into the length L, because density will remain same. If we are considering this as a wire and of resistance R, its length is L, area is A. So when we will stretch it, length will change with respect to area, or we can say length is inversely proportional to area. So in this way we are calculating here that length is inversely proportional to radius square. or we can say L1 upon L2 is equal to R1 upon R2 upon R1 whole square. This is equation number 2. Finally, we are getting, when we put this equation 1 and equation 2, we are getting power P2 upon power P1 is equal to N2 upon N1 whole square. Radius relation would be twice, then R2 upon R1 power 4. So it is given over here in the equation that ratio will be quadruple. So means N2 by N1 is equal to 4 times. Also R2 radius upon radius 1 is equal to 1 by 2. On substituting this value over here in the main relation, we are getting P2 upon P1 will be around 4 times square into 1 upon 2 to the power 4. So this is equal to, yes, 1. So means power will remain same. It is reflecting over here. So option B is the right answer. Key concepts used in this question is power P equal to V square upon R. Also EMF is directly proportional to number of turns. Radius R equal to rho L upon A, and that is it. And also we have mass is equal to rho into V. So we have 5 formula used in this question, but it is just a general very easy question. That power equal to V square upon R. V is the EMF, that is directly proportional to number of turns, and R is the radius, that is equal to rho L upon A. Area is pi R square. So in this way we will find a relation and we will put over here. Now question 4 is related to an infinitely long cylindrical conducting rod is kept along z-axis. A constant magnetic field is also present in z-axis. Then current induced will be, an infinitely long cylindrical conductor rod is kept along z-axis, x-axis, y-axis, z-axis. So means if we consider this is the rod placed along z-axis, we can see the diagram like this. Positive z-axis, a constant magnetic field is also present along z-axis. So means magnetic field is along z-axis. This is this. We need to find the current induced in it. Current induced in it. So we know that as it is in the same direction, because induced EMF is equal to induced current is due to induced EMF by resistance R. R would be there because we consider cylindrical conducting rod. So it is equal to delta phi upon delta T divided by resistance R. And delta phi is due to the change in magnetic field because area is same. So change in magnetic field, either magnetic field should change or area must change. But in this given question, magnetic field is not changing, it is given uniform, and area is not changing. So we can say change in flux is as 0. Definitely induced current will be induced. So we can say option A is the right answer because no flux change, no induced EMF, no current. So this question is based on law of Faraday's induction concept. Last question we would like to discuss with this, question number 5. A circular loop of radius R carrying current I lies in xy plane with its center and origin. The total magnetic flux through xy plane is. So total magnetic flux. So total magnetic flux can be is equal to the magnetic field into the area. Now a circular loop of radius R carrying current I lies in xy plane. So let wire is in this direction, that is wire carrying current I in xy plane with its center at origin. The total magnetic flux through it using right hand Fleming rule, that magnetic field would be into the plane and it is out of the plane, and then the total magnetic flux through the xy plane is. So total magnetic flux through the xy plane is. So total flux is B into area, and the xy plane. Field lines, we know that field line are parallel to the plane of loop. So as these are parallel to the loop, so we can say ideal sine theta upon r square, and we dot a from this, so it is cos of theta. We can over here, so as theta is 90 degree, so definitely flux would be 0. So this question is based on here. We have to find out direction of magnetic field, and it is in the means magnetic field lies in the same plane as the area. So the flux will be equal to 0 because cos 90 is equal to 0 as B and A forms theta is 90 degree. So the key concept uses phi equal to B into A. Or either we can use the formula set magnetic field in vector form, area vector, then we will find out theta as theta become 90 degree, so flux involved will be 0. So option D is the right answer. So in this segment we would as we discussed self-induction, mutual inductance, flux, induced EMF, induced current, all these. So basic questions were discussed. Ask IITians brings you a very good opportunity to paste your questions regarding the subject. What you need to do? First of all, select www.askiitians.com, then choose Ask a Question link. After that, you will reflect a discussion board where you can post your questions. After that, you need to go for Select Category. If you want to paste a questions regarding electrostatic, choose the concerned link, then type your question. After typing the question, select Get Answer. Then you will find the answer of your question within 24 to 48 hours. In this part, we discussed previous year questions asked in different examinations. Now we would summarize the complete chapter, electromagnetic induction, what we discussed in all parts. In first part, we discussed magnetic flux. Then we discussed Faraday's laws of electromagnetic inductions. Then we switch to the concept of Lenz's law and its applications, and then we find out types of electromagnetic induction as self-inductance and mutual inductance. In case of self-induction, we consider the case of solenoid, finding its inductance value. Then we switch to finding self-inductance of a toroid. Now we switch to mutual inductance. In case of mutual inductance, we find out mutual inductance of two coils connected to each other, maybe parallel, maybe series. After this, we switch to energy part, finding energy of a coil, and then we switch to the drawback part like eddy currents. Then we switch to the concept of application part like induction stop, electric generator, induction motor, and transformer and its applications. For more videos of physics, chemistry, mathematics, and biology, stay connected with Ask IITians. Thank you.